talk about section 8.6 and 8.7. And the topics of these two sections are, in 8.6, we've got functions as power series. And in 8.7, we have Taylor and Maclaurin series. All right, so you might be wondering what's going to happen for the rest of the semester. And today we're going to finish up Chapter 8. And if we have time, then I'm going to start to give you an introduction to Chapter 9. Chapter 9 is two topics, parametric equations and polar coordinates, that are important subjects for Calc 3. And so I'm going to be giving you an introduction into those topics. We're not going to go delve too deeply into them, just basically enough to say, here's what they are and here's how you work with them. And once we're finished with that, then we'll be done for the semester. All right, so that is our schedule for the final few classes. Okay, so 8.6 and 8.7. So we've actually seen a function that's been written as a power series already. We've seen one function, and that function is f of x equals 1 over 1 minus x. So we've seen one function written as a power series. And the way that worked was that 1 over 1 minus x was exactly equal to 1 plus x squared plus x cubed plus x to the 4th plus x to the 5th. And this pattern continued forever and ever and ever. And so we could represent the function 1 over 1 minus x by this infinite power series. And the only thing that we had to remember about this was that this was only true for x values between -1 and 1. So we could take this infinite power series, and this infinite power series converges to 1 over 1 minus x, as long as the x values are between -1 and 1. Now, this particular power series is a power series that over the next week you should write down and maybe post it on your refrigerator so that you have something to look at every time you go and grab a snack. Or if you're really careful about brushing your teeth often during the day, you might write it on your bathroom mirror in a whiteboard marker so that you can remember this power series. My point is you would have it memorized. Okay, so the thing is that right now, this is the only example of a function written as a power series. But just knowing this piece of information, we can use a little bit of cleverness and come up with a bunch of other functions that we can write as power series. So we can be clever and write the power series representation for other functions as well. So here's our first example. So 1 over 1 plus x squared. All right, so when I look at that, it kind of looks like 1 over 1 minus x, but not exactly. There are a few things that are wrong with this. For example, I've got a plus sign instead of a minus sign, and I've got a square on the x instead of just an x. But if I kind of mold this a little bit with my hands, I can kind of make it look like this form, 1 over 1 minus blah. So that's what I want to do up here. So I can rewrite this as 1 over 1, and if I want to have a minus sign there, how do I adjust that? Yeah, minus and negative would work. And so I can rewrite this as 1 over 1 minus a negative x squared. Exact same function, just tweaked it a little bit, dressed it up a little bit. And what this does for me is that now I've written this function as 1 over 1 minus stuff. And so I can go back over here to this power series that I know, and everywhere that I see an x, I can replace it with that stuff. I can replace it with a negative x squared. So check this out. I can write this as replace x with negative x squared in the power series for 1 over 1 minus x. So we end up with 1 plus x, but instead of an x, I'm going to have a negative x squared, plus x squared, which is negative x squared, plus negative x squared raised to the third, plus negative x squared raised to the fourth, plus dot, dot, dot. Are there any questions about what I'm writing down there? Not necessarily why or how or anything like that, but where those values are coming from. Okay, so I've now written all this stuff down. This doesn't quite look like a power series because our definition of a power series is that we have a number plus a number times x plus a number times x squared, etc. And so we need to rewrite this so that we have a coefficient times x raised to a power. So in terms of simplifying this, I've got a 1 minus x squared. Now when I square the negative here, it goes away, so I have plus x to the fourth. Now I've got an odd power, so I've got a minus, and then x to the sixth. And then plus x to the eighth. And what's my next term going to look like?
Minus x to the 10th.
Yeah, minus x to the 10th will be the next one. And then a plus x to the 12th, etc. And so what we've done now is write 1 over 1 plus x squared as a power series. So now I've got an entirely new function written out as a power series. Now, this is not an overly complicated function. However, this function that I have right here, if I wanted to approximate it, I could cut off my power series maybe after the second term and use 1 minus x squared to approximate 1 over 1 plus x squared, and that would be an okay approximation. Okay, so I've got this series, and I also would like to know where this series converges. And so I know that my original series converged where x was between negative 1 and 1. That was a good question?
No, I was just...
Okay, got it. Okay, so my original function converges between when x is between negative 1 and 1, but we replaced x. And so this series converges when that new stuff, the negative x squared, is between negative 1 and 1. And so that means that now I need to solve this equation for x. Or not this equation, this inequality for x. So the first thing I want to do is to divide by negative 1 to get the negative away from the x squared. What do I have to remember when I divide by a negative? Yeah, I have to flip these signs around. And so when I divide by negative 1, I end up with 1 is greater than x squared, which is greater than negative 1. All right, so now when I look at this thing right here, I still want to solve for x. There's some weird things going on. Like, for example, x squared. Is that always greater than negative 1? What do we know about squares?
They're positive.
Yeah, they're always positive. So really what I'm looking for is this number down here doesn't really make sense. So I might bump that up to a 0. And I might say, okay, well that means that... Well, that means that x squared has to be less than 1 and greater than 0. Or I could leave it just as it is right there. But either way, what I need to know is that my x squared term will be between 0 and 1. If I take the square root, then I get that x is between 0 and 1. So my series converges, my interval is slightly smaller, but otherwise we're all good. Okay, any questions or comments about that? Alright.
Why'd you take out the negative?
Yeah, that's a good question. Let's rethink this one a little bit, that part of the question. So, alright, so we've got negative x squared is between negative 1 and 1. So maybe we should think about this slightly differently. I'm going to erase that. Let's go back over here and say, okay, we've got negative x squared between negative 1 and 1. Divide by negative 1 on all sides, so that means I gotta have to flip everything. So I now have 1 is greater than x squared, which is greater than negative 1. Okay. And so maybe a better way to think about that, maybe what I was just thinking about is not the easiest or best way to think about this. So I could leave this just like it is. If I take a square root, that's not going to make sense. So what I could do here, because of this even power, I could write this as the absolute value of x squared is less than 1, and I could leave it like that. Or I could leave it as it is up here. So I think that's probably a better thing to do than to mess around with the 0. All right. Questions or comments about that?
So you're just kind of like sweeping the complex answers under the rug.
I am kind of sweeping complex answers under the rug. Yeah, we don't want to deal with this.
So then, that's a better one than the 0.
So we have a couple of options. One is that we can say, okay, this series will converge as long as x squared is between negative 1 and 1. Okay. And so that's going to work. And actually, it's a more valid answer, is this one right here, because what I was doing with that 0 was me being on track. So you should erase that part about the 0. Okay. Ignore that part and go back to this idea.
So then it's this absolute value x squared is
Absolute value of x squared is less than 1. Yeah. So I think my 0 idea was not a good idea. So cross that one off. All right. Any other questions about what I just confused you on right here? Going once. Going twice. All right.
Is absolute value of the squared quantity redundant though?
It is a little bit. So the absolute value of a squared quantity tells us that you could then say that the absolute value of x is going to be less than 1.
So there'll always be positive for the squared.
Well, this value up here will always be positive, but then, for example, negative 0.5 would also work. When you square it, you still have an absolute value less than 1. Yeah. All right. Let's look at a second example. I have to tell you something about this particular problem. When I was thinking about what I wanted to do, when I wrote down my example, and I said I was going to do this one, and then I said, no, I don't want to do the square because I don't want to deal with this inequality issue that pops up at the end with the even powers. So I changed it to 1 over 1 plus x cubed, and that's actually what I wrote down on my paper. And then when I wrote it up on the board, I wrote the x squared term anyway, and so we had to go through that silliness with the inequality. So anyway, all right, there's our first example. Here's our second example. All right, so I look at 1 over 1 minus 2x. And I'd like to write a power series for this function. All right, now at this point, we know exactly, well, okay, I guess technically we now know 2, but we really know one basic function and its basic power series representation. And so when I look at this, this kind of looks like one over 1 minus x, which we know is 1 plus x squared plus x cubed plus x to the 4th plus etc. And so what I'd like to do is make this guy look like 1 over 1 minus stuff. And so in this one, this is actually a lot easier, right? Because I already have my minus sign in here. And so my stuff is my 2x. So everywhere up in the original series that I see an x, I'm going to replace that with my stuff, which is my 2x. And so I've got 1 plus 2x plus 2x quantity squared plus 2x quantity to the 3rd plus 2x quantity to the fourth plus dot dot dot. And so here's my power series. Any questions about what I wrote down right here?
So you could always do that, if there's just a number in front of the x, that's just your stuff.
That's right. Whatever, as long as you can write your function as 1 over 1 minus stuff, as long as you can group that stuff into parentheses, you can do this replacement. Okay, now we're not quite done with this one now. We now need to clean this up so that we have number times x raised to a power plus number times x raised to a power. So in this case, I've got 1 plus 2x plus 4x squared plus 8x cubed plus 16x to the fourth plus dot dot dot. And so this is my power series representation of 1 over 1 minus 2x. And this one is going to converge when our stuff, so converges, when our stuff, which is 2x, is between negative 1 and 1. And this one is way easier to solve for x. So I can divide everything by 2. And I end up with converges when negative 1/2 is less than x, which is less than positive 1/2.
Is it always going to be between -1 and 1?
Yes, because the original series converged when x was strictly between negative 1 and 1. So because we know that already, then we can always use between negative 1 and 1. Now some other examples that we're going to see in about 10 minutes, the answer will be different, but for series that look like 1 over 1 minus stuff, this is the case. Okay, so this is really cool. We can take a function, mildly crazy function, and write it using its power series representation. Now, why is that possibly useful? Well, for one thing, I can approximate this. Okay, this is not an overly crazy function, but it's just our first couple of examples. I can take a crazy function and write down its power series representation, chop it off, maybe after the second term, and use 1 plus 2x to approximate 1 over 1 minus 2x between negative 1 and 1. Or I can make a better approximation by adding on one more term, or an even better approximation by adding on another term. And so I can do this, and I can be as accurate as I want to be, but this polynomial is easier to deal with than the fancy 1 over 1 minus 2x. So for those of you that are going to go off and create crazy complicated functions, these power series representations of those functions, those are what you're really going to be using. You're not going to be using those wicked crazy functions. You're going to be using power series representations and then cut them off somewhere along the way. Okay. So now we can look at any kind of function. You're walking down the street and a function pops out of the dark alley and it looks something like 1 over 1 minus stuff. Or if you can manipulate it and knock it around a little bit so it looks like 1 over 1 minus stuff, then you can use this power series. But there's an awful lot of functions that don't look like that. I can think of, for example, sine of x, e to the x, natural log of x. None of those look like 1 over 1 minus x. So what do we do about those functions? What about other functions? All right, to answer this question, we need to write down a theorem. And the theorem says, if f of x has a power series representation in this case, we're looking at examples that are centered at x equal to 0. So if our function has a power series representation centered at 0, then that power series representation looks like c0 plus c1x plus c2x squared plus c3x to the third plus c4x to the fourth plus dot dot dot. And so if f has a power series representation that looks like this, then there's a really, really handy formula which tells us exactly what these coefficients should be. So if that's true, then the nth coefficient, Cn, is equal to a fraction whose denominator is n factorial and whose numerator is the nth derivative of the function evaluated at 0. And if f of x has a power series representation centered at x is equal to a, then we can write f of x as c0 plus c1 times x minus a plus c2 times x minus a squared plus c3 times x minus a to the third plus dot 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 where Cn, the nth coefficient, is again equal to a fraction whose denominator is n factorial and whose numerator is the nth derivative of f evaluated at a. All right, so what I've just written down here is a pretty wild and really strong theorem. It says, you know what, you can take any function that you want, and as long as that function has a power series representation, then we know exactly how to find the numbers that go in front of the x's. And the way we do that is that we use the given formula. It says the nth coefficient is the nth derivative evaluated as 0 divided by n factorial, or if we're centering at an x value other than 0, then our coefficient is the nth derivative evaluated at that center point a divided by n factorial. And so these two types of series have a name, and this one down here where you have a power series that is centered at x equal to a, this type of series is called a Taylor series.
Right.
And in the special case where the power series representation is centered at x equal to 0, then this one is called a Maclaurin series. So you've got this Maclaurin series, you've got a Taylor series, two different mathematicians. Taylor, the mathematician, his idea is actually the generalization, because you can say centered at a and you let a equal 0 and it covers this whole category up here. But Maclaurin did a lot of work strictly centering at x equal to 0, and so he gets his name associated with those, even though it's just a special case of the Taylor series. Okay, so let's look at an example. So our example, we're going to start by finding a power series representation centered at x equal to 0 for the function f of x is equal to e to the x. Okay, so we've got this function f of x is equal to e to the x, and we would like to write e to the x as a power series. And so the way it'll look is e to the x is going to be c0 plus c1x plus c2x squared plus C3x to the third plus C4x to the fourth plus dot dot dot, where Cn is the nth derivative of our function evaluated at 0 divided by n factorial. Alright, so we need to figure out C0, C1, C2, C3, C4, C5. So this sounds like a job for a table. So in order to figure out all of these coefficient values, I'm going to create a table, and my first column is going to be the n value. And so we'll have n equals 0, 1, 2, 3, 4, 5, and hopefully after we get to 5 we'll have a nice pattern going on. Alright, and so our first column, when C equals 0, we want to figure out what C0 is equal to, and then we're going to want to figure out what C1 is equal to, etc. So my formula says, okay, I'm going to need an nth derivative, and then I'm going to have to evaluate that derivative at 0. So my next column here is going to be my column that talks about the nth derivative of our function. So the 0th derivative, that's just the original function. You haven't taken any derivatives yet. So the 0th derivative is e to the x. So f of x is equal to e to the x. Okay? So then we'll take our first derivative. We have f prime of x. What's the derivative of e to the x?
We're going to have a lot of e to the x's in that table.
I think that you are absolutely correct. So we've got an e to the x. I take my second derivative. And I get e to the x. And I take my third derivative. And I get e to the x. And I take my fourth derivative, and this is about the time where I get tired of writing those little hash marks. And so I write my little 4 inside parentheses, so this is telling me I'm taking the fourth derivative. And that fourth derivative is e to the x. And my fifth derivative is also e to the x. Alright, so lots of derivatives, but they all happen to look exactly the same. Okay, so now once we've got those derivatives written down, I don't actually want the derivative evaluated at x, I want the derivative evaluated at 0. So once I have each of these derivatives, I can plug in 0 for x. So we'll look at our nth derivative evaluated at 0. So f evaluated at 0 looks like e to the 0, which is 1. And we're probably going to get that same value the entire way down. Our first derivative, f prime evaluated at 0, is also equal to 1, etc., etc., etc. All right, are there any questions about coming up with our nth derivatives? Okay, so the final column in my table is going to be the column that is the most important column in terms of what we're looking for. That is the coefficient column. So C0, we're going to take that nth derivative and we're going to divide it by n factorial. So here we have 1 over 0 factorial. I'm going to come back to that one in a minute, because what the heck does 0 factorial mean? We'll put a big question mark on that one. How about C1 is 1 over 1 factorial. C2 will be 1 over 2 factorial. C3 will be 1 over 3 factorial. C4 is 1 over 4 factorial. And C5 is 1 over 5 factorial. Okay, now these numbers down here, 5 factorial, that's 1 times 2 times 3 times 4 times 5. And these all are good. 1 over 1 factorial, that's 1 divided by 1. And so C1 is exactly equal to 1. Now, if you have your calculator, please pull it out.
Isn't that the series that ends up being the sum of the 1 over the factorials?
And you'll see that happening here in just a second. Okay. And on your calculator, you have a factorial button. And if you're not sure where that is, check with your neighbor and see if your neighbor can describe where it is.
Oh my god.
So if you have an 84, then what you should be looking under is 0 factorial is equal to 1. And what is the reasoning for that? Well, quite honestly, the reason that 0 factorial is equal to 1 is because it's what makes patterns work nicely. Okay? And so this is by definition. So 0 factorial is equal to 1, and so we have 1 over 1, which is 1. So our C0 coefficient is a 1. And I have no better reasoning on that than it makes the patterns look pretty and work well. Okay, so our goal is to find a power series representation for e to the x. And we just created this entire table over here to fill in each of the c values. And so we can write down that e to the x is equal to c0, which is 1, plus c1, which is also 1, times x, plus c2, which is 1 over 2 factorial times x squared. C3 is 1 over 2 factorial times x, and then x cubed. Then we have 1 over 4 factorial times x to the 4th, plus 1 over 5 factorial times x to the 5th, plus continue the pattern. And so this is our power series for e to the x. Oops.
Oh, I get it now.
Okay. All right. So are there any questions on coming up with these values? Okay. So I might rewrite this and clean it up a little bit. This is the way that you'll most often see this series as 1 plus x squared over 2 factorial plus x to the 3rd over 3 factorial plus x to the 4th over 4 factorial plus dot dot dot. And if you don't like to write your series out in longhand like this, then you can also write this using summation notation. And so we have the sum where n goes from 0 up to infinity. And what I notice about the terms on the top is that I have x raised to the n divided by n factorial. And that works even for n equal to 0 because of that nice little, by definition, rule that 0 factorial is equal to 1. And so this is our power series representation for e to the x. And because this power series representation is centered at x equals 0, this is also called a Maclaurin series. So now you've got two separate series. You've got a function 1 over 1 minus x that's represented by the power series. And then you've got this e to the x function also represented by a different power series. You should add both of those onto your list and post them both in your refrigerator. Okay, so here's our power series for e to the x. The next question, which we'll address after the break, is, okay, our last power series converged when x was between -1 and 1. For what values of x does e to the x converge? And so we'll ask that question after the break. So please take a 10-minute break, thanks to mathematician Maclaurin. But on the other hand, another way to say this is that e to the x has a power series representation given by this series. So either way, if you want to acknowledge the mathematician, you call it a Maclaurin series. If you just want to call it a generic power series, then you can do that as well. Right, so one thing that Mark mentioned earlier was, he said, oh, you know, e is equal to 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus dot dot dot. That this is one way to write the letter e as this infinite sum. And we actually get this expression here as from this particular Maclaurin series. If you allow x to be equal to 1, then you have e to the first, which is just e, and then you have exactly this sum over on the right-hand side. And so the number e, this irrational number e, 2.71 blah 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 blah, is exactly equal to here's your 2, and then this is your 0.71 blah 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 blah.
I know they talk about how E is used to like model certain things. Is that because that can be used to model certain things, and that's where they use the value of E?
That is one reason. E actually shows up in a bunch of different places. So besides being able to approximate E by cutting off this particular series, E also has another version that comes from a compounding interest formula. And so there's a limit of, and again, I don't know the exact formula, but it's roughly something like 1 plus n raised to the 1 over n. And if you take
1 over x to the x. It's the limit of that side.
1 plus...
That quantity there traced to the x. That's the compound interest.
And so, yeah, so it turns out that this expression is also equal to E, and so as x goes to infinity, then this compounding interest formula, or portion of it, turns into E, and you get a continuously compounding interest formula. So you can model stuff there. We can also model stuff with populations which work in the same way, like continuously compounding interest. So E is a pretty rad number. Okay, other questions or comments about E?
Is there an interval on this one?
That's the next question. So now the next question is, for what values of x does this power series converge? And what do I mean by the power series converging? Well, I want to know when does this series converge, and in particular, for the values of x where this series converges to e to the x. So for what values of x does this power series converge to e to the x? Well, to answer that question, here's my power series written in summation notation. And if I want to figure out for what values does this series converge, what test do I want to use? Yeah, I want to look at the ratio test. And so the ratio test says that I'm going to take the limit as n goes to infinity of the an plus first term divided by the an term and take the absolute value of that.
And that's because on the thing you got a power and then in the base, n in power and in the base.
So I've got so the reason I want to use the ratio test is because I've got an n that's part of my power, and down here I even have a factorial. So both of these things are reasons for me to use the ratio test. Okay, so let's write this out. We've got the limit as n goes to infinity. The n plus first term, well, I'm going to cover up my series symbol and replace n with n plus 1. So I've got x to the n plus 1 divided by n plus 1 factorial. And then I'm going to take that and divide by the nth term. Now, dividing by the nth term is the same thing as multiplying by the reciprocal of the nth term. So I'm going to go ahead and do that right away. We've got times n factorial over x to the n. And then I need absolute value bars around all that. Any questions about writing that part down? Okay, so now I can start to simplify a few things. I've got the limit as n goes to infinity. X to the n plus 1, I can rewrite that as x to the n times x to the first. N plus 1 factorial, we can rewrite as n factorial times n plus 1. And the last part, I don't do any rewriting on it. Okay, any questions about how I've rewritten that? All right, I can start to cancel some things. The x to the n's cancel, the n factorial cancels, and we are left with the limit. And I'm going to leave my series up here down at the bottom for a little bit longer. But we are left with the limit as n approaches infinity of x over n plus 1. And I still have my absolute value bars. So when I look at this, in the eyes of my limit, this x is a constant, so I can pull that out in front. And so I have the absolute value of x times the limit as n goes to infinity of 1 over n plus 1.
We don't need the absolute value signs there though.
On the 1 over n plus 1, no, I don't need those there anymore. I could just write those as parentheses because the 1 over n plus 1 is always positive. Okay, so now I look at this, and this absolute value of x comes along for the ride. As n goes to infinity, what happens to 1 over n plus 1?
0.
Goes to 0. And so we have absolute value of x times 0. Anything times 0 is equal to 0. And so for what values of x is 0 less than 1? All of them, yeah. So 0 is less than 1 for all values of x. Which means that this series, e to the x equal to 1 plus x squared over 2 factorial plus blah, 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 converges. So the series converges for x between negative infinity and positive infinity. So this series converges for all values of x. So we do not have that fixed window from x going from negative 1 to positive 1. This series converges for the entire number line. So the more terms you add on, the closer this power series looks like e to the x. And it works forever and ever and ever in both directions. All right, any questions or comments about that? Okay. All right. So I'd like to look at one more example of one of these power series. And so in this example, we would like to find the Maclaurin series, aka power series centered at x equal to 0. So find the Maclaurin series for f of x is equal to sine of x. Okay, so we're given our function f of x equals sine x, and we'd like to write down a power series to represent sine of x. So what that theorem told us was that if sine of x has a power series, it looks like c0 plus c1x plus c2x squared plus c3x to the third plus blah, 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 where cn is equal to the nth derivative evaluated at 0 divided by n factorial. Okay, so we need to figure out all these c values, so I'm going to create another one of these tables. So my table, the first column will have the n values. And for this example, I'd like to look at n values starting at 0 and going all the way up to 8. 0, 1, 2, 3, 4, did not leave no space. 1, 2, 3, 4, 5, 6, 7, and 8. All right, so our next column will be our derivative column. And so our 0th derivative, that's the original function before we take any derivatives, is sine x. And so what I'd like you to do right now is I'd like you to turn to one of your neighbors and I'd like you to say hello to one of them. Maybe two of them. And I would like for you and your neighbor to fill in the derivative column and then the derivative column evaluated when x is equal to 0. The 0, sine of 0 is 0. What's the cosine of 0?
1.
Yeah, so we have 1, and then we've got a 0. Negative cosine of 0 is negative 1. And so we're going to repeat this pattern of 0, 1, 0, negative 1 all the way along.
So to come
No.
off here.
And so these are going to be the numerators for our coefficients. Okay, any questions about any of those values? Okay, so our final column in our table is the Cn column. And so we have 0 over 0 factorial, that's our C0. C1 will be 1 over 1 factorial. C2 is 0 over 2 factorial. C3 is negative 1 over 3 factorial. C4 is 0 over 4 factorial. C5 is 1 over 5 factorial. C6 is 0 over 6 factorial. C7 is negative 1 over 7 factorial, and C8 is 0 over 8 factorial. Okay, so we've got all of these values. Now every single one where we have a 0 in the numerator, 0 divided by any non-zero number is 0. And so our C0 is 0. And so all of our even coefficients are going to have a value of 0. Okay, so now when I go back over here to my series, I'm going to write sine of x. And whenever I have the 0 coefficient, I don't even need to write that term down. So for example, I don't need the 0 for the C0. And then I have plus 1 over 1 factorial, which by the way is equal to 1. And so I have 1 times x. The C2 coefficient is 0, so I don't need to write that one down. C3 is negative 1 over 3 factorial times x cubed. My C4 is 0, I don't need to write it down. C5 is 1 over 5 factorial times x to the 5th. C6 is 0, so I don't need to write it down. 7 is plus negative 1 over 7 factorial times x to the 7th. 8 is 0. What do I expect in terms of my pattern for my 9th coefficient?
1 over 9.
Yeah, 1 plus, so it would be plus 1 over 9 factorial times x to the 9th, and then plus dot 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 dot. So if I want to clean this up a little bit, I can write this, and this is typically the way that you'll see this, is sine of x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial minus dot dot dot. And so this is my power series for sine x. And if I want to write this in compact summation notation, then this series looks like the sum where n goes from 0 up to infinity. And I only want the odd numbers, so I want to skip every other power. So the way that I'm going to make that work is I'm going to look at this as x to the 2n plus 1 divided by 2n plus 1 factorial. And you can double check that when n equals 0, you get a power of 1. When n is equal to 1, you get your power of 3. And so by looking at this powers as 2n plus 1, that helps us to get just the odd numbered powers. And so this is our series for sine of x.
Let's say you give us a test. Do you want us to do it some? Which form would you want us to do?
So that's a good question. So this is series number 3 that you want to add to that list. And so this is a Maclaurin series, and everyone just quickly wrote something down in their notes. So this particular series, if I said, okay, write down the Maclaurin series for sine x, you could write it out in the longhand form or the shorthand form, whichever one you prefer.
And then you're only using the odd terms because equal 1 through 0.
That's correct. That is correct. Yes, I could have written, 0 times x squared, but that would be silly, so I didn't do that. All right, so a couple of comments about this particular series. The first comment is that notice we do only have the odd powers, okay? And by the way, the sine function, if I draw a picture of it, the sine function is an odd function in the sense that the symmetry is across the origin, so if you fold and then fold again, then your function lands back on itself. And so sine of x is an odd function. That phrase odd function comes from the fact that Taylor series, the expanded Taylor series or Maclaurin series or power series, because this series has strictly odd powers, that's where the name odd function comes from. So when you learned that back in college algebra, we just said an odd function is a function that if you fold across the y-axis and then across the x-axis, the function matches on itself. That's not the real reason it's called an odd function. It's called an odd function because the power series representation has only odd powers in it. Okay, so this is sine of x. Now, there is one more series that we need to talk about, and that's cosine of x. But before we talk about cosine of x, I'd like to take a look at a picture of our sine x function. F of x is equal to sine x. And then if you go down 2 lines, you'll see this sk, which is my partial sum. And so I've written, oh, you guys, time out, hold on. Okay, so this should be -1, 2, let's see here, we need for n equal to 0, we need a positive 1. So -1 times x to the 2n plus 1. So please fix that in your notes. You need a -1 in there to make this alternating. I totally forgot about the alternating part. Okay, so you guys all change that? And you can backlog that on the YouTube too. Second term after the third term. And so these are our partial sums. And so then I'm going to write a table of these partial sums. And you can see that each time we're adding on one more term. Okay? We're alternating between pluses and minuses. We have only the odd powers. And the denominators are actually expanded out as opposed to leaving them as, 3 factorial, 5 factorial, etc. All right, so here's what we've got. We've got our sine function, that's the blue curve. And right now, we have a picture of our power series expansion that gets cut off after y equals x. If I hit the plus button on here, well, not this plus button, this plus button, okay? Now I'm cutting off after the second term. And so each time, as that slider moves forward and as this number goes up, we're going to include more and more of these terms. The more terms we add on, the closer our power series expansion gets to the function y equals sine x. So if I want to approximate y equals sine x between -15 and +15, let's see, it looks like, based on this picture, oh, we're nearly there. When I include 19 terms on there, then it looks like I've got something that looks just like sine x between -15 and +15.
We talked about with trapezoids that you could use that one formula to figure out how many subintervals you need to be within somewhat of an accuracy.
Yes.
Is there some sort of a formula that you can apply to a series to figure that out so you don't happen to have Mathematica?
Right, so that's a really good question. The answer is yes. And where that comes in is when you have series that are alternating series, then there's a formula that says that if you chop off at a particular value, then your error will be no worse than the value at which you've chopped off. That only works for alternating series, but sine of x, for example, is an alternating series, and so that works out well there. So yes, there are and a variety of other error bounds for other types of functions as well. Okay, cool. So this is our power series representation of sine x. Okay, other questions about this particular example? Notice that every single time we have an odd function because every single one of these powers are odd, so we always have our curve going off in opposite directions. In Taylor series, I did not do an example with with a Taylor series, but what I'd like you to take out of this particular section is that I'd like you to know the following Maclaurin series. So the thing is, Taylor gets all the credit because he talks about centering at places other than x equals 0, but the most important series that we're interested in are the ones that are centered at 0, so we're really focusing on the Maclaurin series even though the overarching title is Taylor series. So know these Maclaurin series. Know that e to the x is equal to 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus x to the fourth over 4 factorial plus dot dot dot. And if you prefer the summation notation, this is the sum where n goes from 0 up to infinity of x to the n over n factorial. Also know that sine of x is equal to x minus x to the third over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial plus dot dot dot. And if you prefer the summation notation, that's the sum where n goes from 0 up to infinity of negative 1 to the n, don't forget that, that's uber important, times x to the 2n plus 1 divided by 2n plus 1 factorial. Now there's also an associated series for cosine of x, and part of your practice problems will be to come up with this Maclaurin series. I'm going to tell you what it is here now, but then I want you to go back during the practice problems and show that make the table for these values. Cosine of x is equal to 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial plus x to the 8th over 8 factorial minus dot dot dot. Notice that for cosine, we end up with all the even powers, and the cosine function is a function that has symmetry across the y-axis, and so the cosine function is an even function. Again, the name even really comes from these even powers on the Maclaurin series or power series expansion. And if I want to write cosine in its summation notation, I look at n goes from 0 up to infinity of negative 1 to the n times x to the 2n divided by 2n factorial. Now we didn't prove this, we did not go through the ratio test for the sine of x, but it turns out that if you test the ratio test with sine x also converges for all values of x. And so all three of these series converge for x between negative infinity and positive infinity. And then the very last one that you should know and understand and love is 1 over 1 minus x, which is 1 plus x squared plus x cubed plus x to the fourth plus dot dot dot. And if I want to write that one in summation notation, I have a sum where n goes from 0 up to infinity of x to the n. And this particular series converges when x is between negative 1 and positive 1. So those four Maclaurin series, power series expansion centered at x equals 0, those four Maclaurin series are ones that you want to know really, really, really well for the final. Okay, so what are some things that we can do with these once we actually know those four series? One thing that we can do is having those four tools in our toolbox we can write down the power series for a bunch of different type of functions. So that big table that we created, you can always go back and use that table. But there are easier things to do. So for example, find the Maclaurin series for f of x is equal to e to the minus 5x. Okay, so option number one, I can look at that and say, here's my function. I could write out, so option one. Option one says, okay, well, e to the minus 5x is equal to c0 plus c1x plus c2x squared plus c3x to the third plus dot dot dot, where cn is equal to the nth derivative evaluated at 0 divided by n factorial. So I could do that and I could create my table and do all of that work. Remember when we created the table, it took up this entire sideboard over here. So we could do that for e to the minus 5x, and that's absolutely positively valid. Or option two, this function looks an awful lot like one of our known series over there. It looks an awful lot like e to the x, except that instead of having an x in the power, we have stuff. So option two is that we know that e to the x is equal to 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus x to the fourth over 4 factorial plus dot 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 dot. And so I know that's true. And I'd like to find a power series representation for e to the minus 5x. So everywhere I see an x, if I replace it with my stuff that's up there, then I've got myself a new power series, and I don't have to go through this entire creating a table method up here. So I've got e to the minus 5x is equal to 1 plus negative 5x plus negative 5x quantity squared over 2 factorial plus negative 5x quantity to the third over 3 factorial plus negative 5x quantity to the fourth over 4 factorial plus dot dot dot. Alright, so now I've got myself a power series expansion for e to the minus 5x. It doesn't quite look right. I do need to tweak a few things and write it so I have a number times x raised to a power. So I can rewrite this as e to the minus 5x is equal to 1 minus 5x. And now when I square on the top here, it cancels my negatives, so I've got plus, and I could write this as 25 over 2 factorial times x squared. And now for the third power, I get a minus, so I have minus 125 over 3 factorial times x to the third. And for my fourth power, I've got plus 625 over 4 factorial times x to the fourth. And now I can kind of see the pattern that's going on. All right, any questions or comments about that one? All right, so here's a bonus for you to think about. Find a power series representation for y equals arctangent x.
For 1 over 1 plus x squared,
So,
never mind, sorry.
no? What is 1 over 1 plus x squared?
Our
When you
son,
brought it up earlier, I was immediately thinking about that, but then
That's the variable.
Yeah, 1 over 1 plus x squared is the derivative of arctangent, and so the antiderivative of 1 over 1 plus x squared is equal to arctangent x plus maybe some constant. So think about this and think about how you might come up with a power series for arctangent of x based on this knowledge right here. All right, so that's something to think about, and I will ask you if anybody has any thoughts on that next time. All right, so I want to wrap up today. First of all, are there any questions on these Maclaurin series / power series representations?
Okay, so how do you alter the summation of e to the x since now that has become an alternating series?
Right, so what you might do is, so this one, if you were looking at the series representation, the summation notation I had, x to the n over n factorial, right? So what I would do down here is I would have the sum where n goes from 0 up to infinity of negative 5x raised to the n
Oh, you just plug that in for x.
over n factorial. And what I would like to do is to actually clean that up a little bit so that in the end, if I rewrite this, I can write this as the sum where n goes from 0 up to infinity of, and I can write this as negative 1 to the n times 5 to the n times x to the n over n factorial. And now I can see where that alternating part comes from. All right, other questions about these power series? Okay. So what we will be talking about on Monday, we're going to start out with this idea called parametric curves. And I want to give you a short preview of that in our final few minutes of class. And when we look at parametric curves, what's really cool about them is that we can draw all kinds of crazy curves. So, for example, in a parametric curve, preview, we have two functions of t, and that first function is a function which describes the horizontal direction, and we have a second function, which we'll call y of t, which describes the vertical direction. So x of t describes the horizontal direction and y of t describes vertical direction. And so what happens is we get something that looks like, for example, x of t is equal to t squared, and y of t is equal to t cubed. So we get some function of t in the x direction, some function of t in the y direction. Now, on your calculator, if you have your calculator, you should pull it out. And if you go under mode, instead of function, cross off function, and click on PAR for parametric. And what you'll end up with is when you click on that, and then you go to graph for y equals, you'll end up with an xt and a yt. And if you plug in t squared for the x and t cubed for the y, and then hit graph, you'll get a picture. Okay. Now, when you look at x equals t squared and y equals t cubed, all I've told you so far is that the x function describes horizontal direction and the y function describes vertical direction. And what you might remember is, you might remember a toy that you might have had where you had two dials. And one dial described the vertical direction and one dial described the horizontal direction. And if you wanted to make a straight line up and down, then you just turned the vertical dial but not the horizontal dial. And same for horizontal, but if you wanted to make a diagonal line, you had to turn both in the exact same speed, and it was really, really hard. And if you wanted to make a really cool curve, then you had to be really specific about how quickly you turn one dial versus the other. And so what we have here is a virtual Etch-a-Sketch. And so what you'll see is these dots here are telling you, going to show you how fast those dials are being turned. One is vertical, one is horizontal. And you can see how those are being turned to create the following curve.
Go to graph. Go to menu. It says graph entry.
So see how fast this is the vertical dial over here, because this path is going up pretty darn fast. So that guy's spinning like crazy. And this guy over here on the right side, this is our horizontal dial. And you notice that that dial, the horizontal dial, is not moving so quickly because we're moving slowly in the horizontal direction. Okay, so we're going to talk more about parametric curves on Monday.